Hello, everyone. Can you hear me now? All right, cool. Welcome. This is kind of a brief slide that you can use if you are talking to anyone in your company about Dora. The website's actually all in English, but this is the Japanese translation of it. If you use this link at the bottom, it just shows a bunch of questions over time, and they're good, thought-provoking questions. This is just kind of a preview. So we'll get into the real talk now, though. So this is me. I wrote a very small book. You can get it in Japanese at the bottom. There are some paper copies, but you'll have to ask Google people for them. I don't know how to get them. Ask Yoshi-san if you know him. He can figure it out, I'm sure. I was an SRE for a long time at Google. I actually ran a team here in Tokyo for a little while. I don't know if any of them are in the audience today or any former Google SREs here. Maybe? Maybe not. There's a few floating around still. Yeah, now I am in DevRel, so I do reliability advocacy, which means I talk on stage about SRE. I like to joke that I tweet for a living, but that's not exactly true anymore. So today we're going to have a very simple structure. We're going to use something called a hook, which is like a simple idea. Then we're going to get into like the real lecture. Finally, I'm going to show you something that I call a lab environment. And then at the end, you can see how you can use it for production. I hope this makes sense to you. First off, can you build a 4-9 system out of 3 nines parts? Yes or no? So you can just think it in your head. You can shout it out. You can raise your hand if you think yes. The beauty of this question is that nobody answers it right away. Everyone always kind of goes, or some people say yes and some people say no, right? I say yes. It's a little tricky, but I want you to think about RAID. So RAID is a bunch of disks that can fail, but a SAN, a RAID array, is a system of those fallible things that has much better availability. So one disk might have 1 9 of availability, but a SAN has like 7 nines or some large amount of 9s of availability. And there's a lot of tricks here on how you do it and the complexity, and yeah, it can still fail, but the complexity adds reliability. We did something to it, and we call that something reliability engineering. That's not what they used to call it when they made RAID, but that's kind of what we call it now. I'm going to do my best to remember what my slides say, because I only know it in English, and it says it in Japanese, so if I'm way off, just let me know. Okay, so this is how reliability used to work in our heads. It still does work this way. So this is the traditional model of building things. So remember the question I just asked you about, can you build more reliable stuff out of less reliable stuff? The answer used to be just flat no. And this is a pyramid to kind of show this. So if you wanted 3 nines at the top, you had to build something on top of 3.5 nines, on top of 4 nines, on top of 5 nines, right? So think of your like your web server needs to be better than your database needs to be better than that, and your cooling and power needs to be even better than that, and your networking needs to be really, really good. So this makes sense. It also is how like gravity works in buildings, and so it's like makes sense in our heads. The weird thing is that scalable internet systems look like this. They look backwards. They look upside down. And what we're doing here is we're actually building, like we said, more reliable systems out of less reliable parts. So this means the bottom of the pyramid has fewer nines than the top. So if you look at something like Gmail or another Google service that has many, many nines of availability, 5 nines of availability, all of the VMs that are running that system have 2 nines. Right? The disks that are holding your data for Gmail have 1 9. So how is it that Gmail is so available and you never lose your mail and it doesn't crash? It's because of the reliability engineering, and it's because of this model. So the key point here also to consider is it used to be the case that the IT team wasn't responsible for the bottom half of the pyramid. So they were responsibility for reliability of the whole system. But in this new model, the IT team is actually responsible for less reliability. It's actually the developers that are responsible for more reliability because they need to build the system correctly to take advantage of these cloud models. So if you're in a team where your IT team is being asked to be responsible for the reliability, like in the old model, but you're living in the new model, you're going to have problems. So the important thing here is pick a side. Either live on the left side or live on the right side. Don't mix them. And if your bosses live on the left and you live on the right, show them this slide and tell them this is a problem. It'll never work. All right, this causes a lot of trouble. For example, lift and shift. Right? If we move something from the old system to the new system and we don't change our way of thinking, the pyramid falls over. Right? We're not taking advantage of everything we could in the new system because our mental model is wrong. We have the wrong philosophy. So we need to address that. And I can't remember what it says at the bottom, but I'm sure it's something clever. But essentially, the IT team won't be able to fix reliability problems in this case. So why is this happening? There's 4 reasons that I wrote in English, but now it says it in Japanese, so I can't read them. But essentially, it's because of distributed systems. So distributed systems are not that new to academia, but they're relatively new to industry, maybe 20 years. So the systems we're working in cloud, the whole point is that they can handle some amount of failure. So if you expect the system to never have any failure ever, you're going to be disappointed, and you're not taking advantage of the fact that distributed systems are meant to have a little bit of failure, and they can handle that failure. You can use that. If you're not using it, you're kind of wasting cloud. I'm sure there's more in there. Customers also expect higher levels of availability now than they used to, things like that, because your competitors are all doing this, right? The big companies are all taking advantage of this. If you're not, you're going to be in trouble. Okay, so why SRE? This comes straight out of the book. This is like core philosophy. You've probably seen this before. Essentially, cost of operation of a system that is growing very high, you don't want the cost to grow with the scale of the system. So if you have a hockey stick curve, like a very good business that goes up and to the right, you do not want your costs to also go up and to the right. What you want is your cost to stay flat. Or in this case, we call it just sublinear. So if you're really good at math, you might want to say your company's profits can be exponential and your operating costs can be logarithmic, right? This gives you a big margin in the middle, and this is what companies like. They like margins, right? And we do this through applying SRE principles and practices, some of which are listed here, I'm pretty sure. A couple points to think about. This is true for any cloud, but this is specific to Google because I work there, is each of the things we call scopes, so these are zones and regions and multi-regional services, they have their own expectations of availability. So this is true for every cloud, more or less. No one does this dramatically differently. So a zone has 3 nines, a region has 4 nines, and multi-region has 5 nines. So there's 2 ways to think about this. You can think of it as the entire zone or the entire region and everything in it. But you can also think of it as a service. Think of like GKE, right? GKE running in a zone, that instance of GKE, the whole system, has that availability. Regional GKE is a different product. It has the next one down. It has 4 nines. So it doesn't take the entire zone to collapse, like physically be destroyed, for you to experience these 3 nines or 4 nines. It might just be for one service. It might be for Cloud SQL. It might be for PubSub. Who knows, right? But they fail in this pattern, and that's important to know about. Okay, so there's a few things. I wish I knew what this said. There's a few things to know about. You want to be able to be aware of these numbers because you want to be able to run away from your problems. You want to know that, a system will fail 3 nines in one zone, but the other zone will survive. right? If you know that this is going to fail in these scoped ways, the important part is one zone tends to fail at a time. One region tends to fail at a time. So if you use 2 zones, this one has 99.9, this one has 99.9, they're a different set of 99.9, right? So it's very unlikely that they will both fail at the same time. So this means that when a failure happens in one of the zones, you can just run away. You do not have to debug it. You can just move to the other zone or the other region. This is very, very powerful. It means you don't have to solve every problem. You can just run away from your problems, because it'll come back later. And in the meantime, just use the other zone. It's fine. Right? You can over-provision. You can scale up in the surviving zone or the surviving region as well. I cannot remember what this says. Generic mitigations. There's a little bit of English to give me a hint. There is it's a very short article. It's written by O'Reilly. It's all in English, I'm afraid. But there's a few of these mitigations that Google SREs have been using for a long time. And one of my colleagues named Jennifer, she wrote this article, and she describes 6 of them, and they're very good. They can be used against any kind of workload in any kind of environment, essentially. But you have to know about them ahead of time, and you have to build them into your system. So being able to take the traffic coming into one cluster and being able to move that traffic to a different cluster in the moment of failure doesn't come out of the box. You have to know that this is a good idea, and you have to plan for it, you have to engineer it, you have to build it. We call this draining. So if you can design your system that allows you to drain any service, you will be in a good position. And I'll show you a little bit more about that in a little bit. There are a few more of these mitigations. They're all described in this article. A few more things. Failures happen in many ways, right? This is my description of how to categorize the failures. And I'll see if I can remember them, because again, I can't read this. So some of them are self-imposed. I made a code change. I made a configuration change. I pushed something bad to production. Oh no, right? Other things are infrastructure, right? So I depend on GKE in US West 2, and it is down right now. Oh no, there's nothing I can do about it, right? These are 2 very different types of problems, but both have the same outcome to your users. The other thing that you can think about is if they are, I can't remember what the columns say, but anyway, the point is the SLOs that you're given by your infrastructure are less than the SLOs that you can offer to your customers, because you can use many parts of the infrastructure. And honestly, your customers don't care what your infrastructure SLOs say. They only care about what you tell them that your service provides. So if you are a bank and you want to have 5 nines of availability, it doesn't matter that your infrastructure supports 3 nines of availability. It can still work. You don't have to tell your customers, oh, my infrastructure only supports 3. That's why we had this outage. They don't care. They want the 5, right? And so, you know, just be aware of this distinction here. I'm sure there's something else I'm supposed to talk about here, but I can't remember. Okay, this is called Dickerson's Pyramid. This comes straight out of the book. You've probably seen it before. An important thing to note here is that this is not like best practice. This doesn't really tell you what to do. This is just areas of work. These are categories of things you would have an SRE team work on. So it's the beginning of what you might work on, but it doesn't really help in detail. But if you've never seen this before, it is a good model to help describe what SRE might look like. If you're doing things outside of this model, make sure you're mostly doing stuff in this model. From the bottom is the most important part. The top is, you know, will come later with maturity. These are some principles. These come straight out of the books as well. The third one there is relevant. Does anyone know what the little red dragon is? That's CrowdStrike. Does that remind anyone of anything? So gradual change would have really helped in the last CrowdStrike outage. I think that's a pretty well understood concept at this point. What happened in that case was they made a global change, and it was just a configuration push. It was actually just a data push. It wasn't even configuration. They uploaded some new data that got pushed to all of their customers at once. In a von Neumann architecture, data is code. Like, you need to gradual change everything. If you have a new language pack, a new translation for a little string somewhere in your code, Do not push that globally, even though it sounds so simple. Everything that goes to production must be done gradually. Remember the red dragon. Okay, so if you're just going to get started, here's my little recipe. If you're just getting started with SRE, and I'll see if I can remember this off the top of my head. Always start with SLOs. If you haven't defined SLOs explicitly, do something like it. You're not going to be able to understand if your system needs more reliability unless you can measure it. And the most straightforward way of measuring things is through SLOs. This also implies an error budget, which means that you know how much room you have to wiggle with. Somewhere in there is also incident response. I don't know which number I'm on at this point, but incident response is the way that you learn about how your system fails. It's also how you learn about what you want to work on next. Once you have a list of things you want to work on next that are based on incidents you've learned from your own failure, that's your engineering backlog, right? You give those to your SREs to work on. You give them these to your app developers to work on. These are the most important things. This is it. It's a simple model. There's more to SRE than this, but this is a good place to start. Okay, let's back up a second though. Bigger picture, it's not just SREs at your company. There's probably other software engineers at your company too. We want to worry about both velocity and reliability. Has anyone here heard of DORA? This is DevOps research. Yeah. This comes from DORA. So in this, we have 4 things you can measure. 2 of them are about velocity. 2 of them are about reliability. Sometimes we call this, it's speed and like stickiness. Like, can you get code out fast? And once you get it out there, does it stay out there? Is it correct? So these 4 things you can measure independent of how you build your system. Then you can start changing your system and you can say, is it getting better? Are we moving faster and are things getting more reliable? And if you make a big change and the numbers go up or get better, then you know it was good. You don't have to guess. If you make a change and nothing changes, that was not the most important thing to work on. So sometimes we make changes because they're cool or we see them at a conference and we install the thing and we run it and we go, did it help? I don't know. But this will help you know if it actually helped. Okay. The other thing that's going on is we have 2 sides of your company, 2 things to think about. One is the app itself. This is the thing you sell to your customers. It's the thing that you really care about as a business. And then you have a platform. The platform is the thing that you do to get your code into production. And if you don't call it a platform today, I don't care. You have one. I guarantee every single one of you has a platform. Even if your platform is open a Jira ticket, we call that paperwork as a platform. Or if it's go talk to Kensuke, that's people as a platform, right? It's still a platform. But what you want to do is you want to start automating this. You want to turn this into code. So here's a little model. I stole this from DevOps, right? The infinity symbol that DevOps loves to use. This is a simple model, right? You want to figure out where you are with the DORA metrics. Choose what you think is your bottleneck. I bet you already know what your bottleneck is today. If you don't, ask your teams. What are we not good at right now? And then invest in it. Either you buy something or you build something, and then you measure it again, and you repeat, 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 repeat. This is a simple model, but seeing it all written out like this seems to help. On the left side is like the developers. So the guy in the blue shirt is a developer, and the person on the right with the green shirt is the platform engineer. This might also be an SRE, might be DevOps, might be IT, might be InfraOps, might be DevSecOps, might be, who knows? You can call them all kinds of names. But here's another view of it, right? The developer works against this thing that runs APIs against clouds and on-prem and whatever. We call this thing an IDP. So this is an internal developer platform. And the developer uses it by making calls over SSH or API calls or whatever. Maybe they write their own tools, but in some way they make a request to this platform, and that platform follows what we call golden paths. So golden paths are your way to implement security requirements or reliability best practices, or we must always do this one check before we blah, 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 or use this database, not that database, right? It's policy. So we don't have to teach the developer every single policy if the platform enforces it. And you're not going to get this perfect the first time, but this is the model you want to go for. So here's an example of some app. Doesn't matter what it says. It's made of components, right? And we have a little thing at the bottom. We're going to call that the platform. I gave it a silly name, Cylon. Does anyone know what this platform at Google is called? No? Borg from Star Trek. Yeah. So it's just a joke, Star Trek joke. But it's composed of a bunch of stuff, right? So this is, it might have like observability, it might have like CI/CD, things like that. There's more to this, but you get the idea. And this is how you might build one on Google Cloud. There's a bunch of options. We just picked some at random. You could have serverless in there. You could have all kinds of stuff you want. Also, you can mix this with third-party stuff, right? You might already have GitHub Actions. You want to keep using that. You want to keep using Datadog, right? You can mix them. This is kind of the beauty of it. It's still your platform, and you can adjust your platform over time. Okay, this is a new step, okay? So once you have a platform in place and you have these golden paths, one of the choices that developers have to make is where to deploy their software. So if you're going to make reliable systems out of less reliable parts, part of the choice is what we call the footprint. So you're not going to run everything in one data center. You're going to run things in multiple zones, multiple regions. You have a lot of choices to make. So instead of just giving them an open book, an open menu of every possible zone and region, follow these plans, okay? So here's some example plans. There's more than 5 of them, but I'm just going to show you a few options. You can kind of get the idea here in that, one is in one zone, one is in multiple zones, blah, blah, blah. So here's the first one. This is very simple. Everyone knows this one already. This is hot, cold. Very easy, right? So the simplest system is just one. The first thing you ever do, if you want to make something more reliable, is just install a second one somewhere else, right? And you have a switch somewhere to switch back and forth. When the first one breaks, use the other one. That's all it is, right? It's easy, easy, easy. This works for closed source. This works for licensed software. There's not a lot of complexity here, but it's not terribly straightforward. You have to do something. You have to notice the failure. You have to push the button. Maybe there's a deployment time. So there's a lag, right? It's not a no-hit situation. Also, if you do this in one region across 2 zones, if the region fails, you're still in trouble, right? So the next step up is going to be more zones and more regions, et cetera. This is how you would build that thing specifically in Google Cloud. So you can see the pattern, right? This is just abstract, and this is kind of concrete. So just by adding one more zone, our SLO has gone from whatever the original SLO was to pretty good, right? 99.98. And this is the best possible SLO you can get out of this model. I call this a ceiling SLO. You can definitely do worse than this, right? You can deploy bad code all day and not hit this mark, but you can get pretty good numbers out of just doing hot cold in zones. But if you want to keep going, you can also keep going here. So there's a bunch of them. Right, here's 5 of them. The white paper describes like 9, but the document that I linked to at the beginning of this shows these 5 in much, much more detail. So, but you get the idea here. It just gets more and more complicated, right? So the beauty of this is you don't need to build 5 different environments. You actually just need to build the biggest one, and all the small ones fit inside that big one. So in this case, I built the one on the far right. If you remember this one, should say like global on the far right. And then I was able to fit all the other ones inside that one. And so some services I deployed globally, like service A, and some services I deployed not globally, like service C is just hot cold. And I can make those choices independent of my infrastructure. My infrastructure is just ready for me to make the choice. And in fact, as a platform engineer, I don't have to make any choices. The app developers can. So I can set up my CI/CD pipeline to let them make this choice. And if they get it wrong because it's too expensive, or they get it wrong because it's not available enough, they can just push a button in the CI/CD and hit enter and redeploy. No tickets, no nothing, just done. So this is the reason why this is important. So there are a lot of knobs in cloud, a lot of things you could possibly change. And if you want to get more reliable, and you have all of these points to choose, it's really, really complicated. And we know that reliability costs money, right? Think of this, the y-axis as yen, right? It's just expensive. Whether it's time or money or complexity or whatever, it's more complex to get more reliability. So the first few steps, you can do a little bit of work and get a lot of reliability. It's kind of great. But later, you have to put a lot of work in, a lot of yen in, and only get a little bit of reliability gain, right? But if you make these discrete points, these 5 discrete points in this case, it's much simpler for your developers to make a choice between all these. If you could imagine it was a continuous curve, they'd always be tinkering back and forth, a tiny bit left, a tiny bit right. But if you make these 5 discrete points and just give them this menu, they can choose go up 1, go down 1. Much simpler. Okay, this is a repo that you can use today. This implements all this stuff. It's not perfect. It's what I call a minimum viable platform. It's a start. You can clone it, you can fork it, you can contribute to it. There are bugs in it, I promise. It is not great. It is not perfect. But it has the beginnings of all this stuff. So you can get started with it. So the idea here was the hook was the very beginning, right? It was that question. Can you build more reliable things on top of less reliable things? We got the lecture about platforms and Dora and all this stuff, right? This repo that I just showed you is a lab. You can download it. You can run it on any Kubernetes system that you want, and you can test things there, right? You don't have to use this for your production system, but you now have a place where you can try out new things, right? This is a lab environment, so you can actually try expanding this platform, or you can try doing different deployment patterns and see if they work for you and your team. And that's when we get to production, is once you take these things you learned by playing around in the lab, not just reading a book, and then you can apply those to your real production system. I'm not sure how I'm doing on time. I have some screenshots of this actually running. Does anyone have a clock? I'm not sure how we're doing. Oh, this is the example here, right? Oh, that's a good point. The last thing was in production, once you get there, make sure you're following the Dora numbers as well. Right? Make sure you're measuring the Dora numbers to make sure that it's growing in the right direction, that the changes that you're making are actually making an impact to your team. Because it's really easy to spend a lot of time working on something that does nothing. It's really, really easy to see that happen, and it's a bummer. That's it for me. I have more screenshots if you'd like to see them, if we have time, or we can do questions. But yeah, that's it. I think we have at least one question so far.
Sure. スティーブさん、ありがとうございました。この後、Ask the Speaker を行います。セッションについての質問や感想は Ask the Speaker にてお願いします。時間、今、そうですか。はい。では、ちょっと時間がありますので、この場でも質疑応答受けようかと思いますが、どなたか質問ある方。はい。
Thank you for your presentation.
Sure.
I'm in charge of senior IT infrastructure engineering manager. So I have one question. I want to know how to improve resiliency. So sometimes redundant infrastructure is more complexity. For example, multi-availability or multi-region. So sometimes we how do I say we had to survey trouble. So I want to know how to improve the resilience.
Okay, resilience is a tricky word. The word resilience in English, to me at least, means that you can cope with new types of failures, right? A system that can handle many types of failures already, we can say that is robust. Different word. But the important part is resilience, you're right, because we have a new emergent behavior that we've never seen before, like CrowdStrike. Right? A new thing happened. We have no playbook. We've never done this before. The system itself cannot handle that. It requires humans, because humans have to investigate the system and understand the new behavior and act quickly. But they also need to be able to, you can't expect heroes, your system engineers, to be heroes and step in and solve it in 5 seconds, right? So this is why we try to give ourselves as much time as possible. And we try to catch failures early. And this doesn't necessarily mean testing, better testing, you know, more QA. Often what this means is gradual change. It means when you make a change to production, change it this much, and then pretend like that is all of production. And look at that. If that one fails a little bit, then it's really easy to recover from that one. And you can investigate this tiny little part of broken production, and your humans can investigate it and learn from it. Meanwhile, 99% of your customers are fine, right? So you're giving your humans a nice little clean area to work in without your customers calling the newspapers, right? So the best thing you can do is learn from your incidents when they're small and learn them in detail. One other soapbox to stand on, please try to avoid the phrase root cause because it's very easy for root cause to sound like the only thing we have to do. But we know in reality there's a lot of things that we have to do. There's a lot of problems with the system. But if you tell your boss, we have a root cause, then once you fix that root cause, you will not be able to work on all that other stuff, right? So instead, there's a phrase we use called contributing factors. This is a list of things. Some of them might be very, very long, very far in the future, right? So do your best to try not to lean on the phrase root cause and instead list your contributing factors every time, over and over, so that everyone knows there's a lot of possible work to do. If you can do that, then your whole system will be more resilient. Does that help?
Okay, I appreciate your answer. Thank you so much.
Thank you.
他に質問のある方はいらっしゃいましたら挙手を。あ、いい感じに。はい。
Thank you for your presentation.
Welcome.
In the presentation, you said the more effort we pay on reliability, at some point, our effort to improve the reliability doesn't pay. So
This is
How-
the graph.
how should we evaluate the effort we should pay on reliability?
So thank you. The effort is time and money.
All of that.
Yes,
all,
all of that
stuff.
together. So it's the easiest way to think about it is how long does it take for us to move the needle on the reliability? The reliability is measured through SLOs. So is your SLO getting higher and higher and higher and higher until it's acceptable? How many 9s are we getting out of our system? If we have 2 today, we want 3, we can measure that. We know how to measure the x-axis. The effort, the y-axis, is measurable through standard engineering management methods. How many people are on the team? How many years does it take to make the change? You know, man hours is sometimes what we call it. So it's basically, there's basically 2 sources of cost. People over time, and infrastructure. So how many VMs, how much storage, how much network, how much blah, blah, blah. Your cloud bill. So you have a people bill and a cloud bill. When you add those together, that's your X or your Y axis. Does that answer your question? Is that what you mean?
Yes.
Okay.
Thank you.
はい。引き続きご質問のある方、先じゃあ奥の方。
Steve-san, thank you for presentation. I'm Tak from dmm.com, which the company in Japan, which the video distributed service.
Cool.
So thank you for presentation. I just, this is a not question, but I just want to see the, so you said some more screenshot of the like labs.
Yeah.
If you yes. So maybe I have the minute or 2 minutes. So
Yeah.
I would you show us to like some screenshot and some like how can I say explanation for this?
Sure.
Thank.
I'm doing it right now. We are on the same page. Good.
Oh, thank
so,
you very
So
much.
this is GKE. So this is clusters in Kubernetes, right? So in this case, I have 6 prod clusters. So it's 3 in one region, 3 in another region. There's a 7th one called config. We can ignore that. That's like an operational management cluster. This is a bunch of services running in those clusters. So you can see there's cart and checkout, and maybe there's another one called front end and add and blah, blah, blah. And you can see that they're running in different clusters on the far right. And you can see which regions they're running on the very far right. So for example, cart is running in 1, 2, 3, 4, 5. I think I just scrolled past it. There should be 6 there. This is what the app looks like. You may have seen this before. Sometimes this is called Hipster Shop or Online Boutique. This is just an example microservices app that you can, it's free, right? This is using, if you've used Istio in the past, this is the view of how the services talk to each other. This also is a little bit funny because this ignores which clusters they're running in. This is the logical layout. So front end is actually at the very top one is running in many clusters, and it talks to like checkout, which is running in a bunch of different clusters. That's not shown here, but it's shown on a different screen. And one example I can tell you about is the ad service is a service that in this app, if you crash the ad service, or if you take down the ad service, the app continues to run, which is good, graceful degradation. So a demo that I like to show, which I can't do today, we don't have enough time, is we can show the system and then I can just kill all of the clusters that are running the ad service as if it was infrastructure, and the whole app continues to run, but there's no ads, which is great because this is, again, graceful degradation. And the reason why this is important to show is because we can run the ad service not in all 6 data centers, but in one data center. So we can imagine if that one data center crashes, we lose ads, but the rest of the system continues to work, and customers don't notice, right? So they're using, the ads is using the first archetype, the simplest one, whereas the front end and the shopping cart are using the 5th archetype or the 6th archetype, the big, expensive one. Right? So this is why we have microservices, is to allow us to make these choices between the services. Some are important, some are less important.
Thank you very much. So you mean like separate the responsibility or some functions and get reliability for these services. I gotcha.
Yeah.
So can I ask one thing, just one thing? So you show me the slide, which one, like topology or we can use, we can see this like topology graph in the GK clusters on the Google Cloud, or we have to insert some like additional components.
So this is, excuse me, this is a product called Anthos Service Mesh, which is, it's managed Istio.
Istio.
So it's a service mesh.
Okay.
So the service mesh is the thing that allows one service to call another service without being programmed on how to find it. It just discovers it through, it actually uses a lot of different methods under the hood, but think of it just as like DNS. So the front end service doesn't have to be configured how to find the checkout service. It just says checkout, and it gets routed to the right place, independent of which one is alive or dead, right? It always finds a happy one.
Okay, I see. So we didn't use the Anthos or something managing Istio. So
Yep.
I didn't see this the web page. So why I can ask you?
Yeah, in open source Istio, you can use a front end called Kiali. I think there's new ones now too, but that was the from maybe 4 years ago.
Yes.
And this show, it's the same thing.
Thank you. I have the experience to use like microservices for a repository on the Google. So I saw that, but I didn't see this in GKE. So thank you very much.
Yeah, you're welcome.
はい、それではお時間になりましたので質疑応答の時間を終了します。改めてスティーブさんありがとうございました。
Thank you.